All right. Hi there to everybody watching the recording. I want to jump into section 10.5 today, which is all about trees. We'll probably get through 10.5 and 10.6. They're all about trees today. So what's a tree? A graph without circuits. Good. So a tree is a graph that is circuit-free. So of course we learned what a circuit was last week, right? It's a walk that starts and stops at the same point, right? Without any repeated edges, right? So if we don't have any circuits in our graph, that's called a tree when it's connected. So if there's just one component of our graph, right, and that graph is circuit free, that's called a tree. Okay. What about a forest? You would assume a forest is similar to a tree, or that it's many trees, which it is. Does anyone, can anyone give me the definition? Good, circuit-free and disconnected. That's exactly right. Okay, cool. Of course, there's also a trivial tree. That's a graph with one vertex and no edges, right? Trivial, remember, is the sort of the easiest one that doesn't really matter, right? So this is a tree. Okay, great, right? But let's do a little bit better tree. So here's another tree. So there's a tree, right? Yeah, that's a seed, right? Very good. Yeah, I agree. That's a seed. That's a tree. And if we take, you know, this sort of situation, and we consider, you know, all three of these to be part of the same graph, right? Then this would be a forest, right? Because you know, we have multiple components that are all trees, so multiple trees makes a forest, right? And the thing that makes a tree or a forest is that it's circuit free. So there's a, you know, if we were to sort of try to ruin this, right? What could we, let me ask the question this way. What could we not do to any of these graphs that would ruin it and make it not a tree anymore? Any ideas there? Put in a circuit, good. And how would we do that exactly? What would we need to add to the graph to make a circuit in that graph? Add an edge, right? Add an edge without a new vertex. Because if I add a new vertex and an edge, well, it's still a tree, right? But if I add an edge between any two existing vertices, like these ones, let's say, if I were to add an edge right there, right? Well, then it wouldn't be a tree anymore, right? So in some sense, a tree, by definition, has the maximum amount of possible edges that it could have and still be a tree, right? Now, if we have a forest, well, then we can add some edges and it would still be a forest. But the only edges that we're allowed to add are what kind of edge? Between what and what? Yeah, between trees. Yeah, between two different components, right? So if I have this set up here, like this whole thing is my graph, these three trees, and I add an edge between two of the trees, well, that's fine. It's still a forest, right? But if I was to add an edge internal to one of the trees, like right here, let's say, right, then that's a no-go. Then I don't have a forest anymore, right? So, if I have a forest and I want to add an edge, the only way to do that and maintain the circuit-free property is to add an edge between components, not inside the same component. Or if I have just a single tree, I can't add any edges at all. If I add an edge, then it's no longer a tree. Yeah, that's right, David. A loop is a circuit, right? So, so if I actually added this one, I would have this little triangle right here. That would be, I think what you're calling a loop, I'm also calling a circuit. Does that make sense? Okay. I don't know what ARA is, but I'm going to take that as a yes. Is that an acronym that I should know? Oh, a reflexive loop. So these trees, they do have to be simple graphs. Well, if they weren't simple, then, oh, I see what you're saying by a loop now. You mean one of these things. Is that right? Yeah, so this loop would make a circuit. So sorry, David, I see what you're saying now, right? Oh, A and then R. Okay, now I get what you're saying, right? So you're going from one vertex back to that same vertex. Got it. So in that case, it would not be a tree because there would be a circuit that just walks over that loop, right? So you don't have to say an additional property that the graph is simple, because both loops and parallel edges both make circuits, right? Because to do the circuit, you walk down one edge and back on the other, right? So those are definitely excluded. Does that make sense? Yeah, cool. Great question. Yeah, so they do have to be simple by virtue of their being circuit free. Cool. Okay. Thanks for jumping in, helping with that. There are quite a few uses that people have thought of for graphs. And your book gives a couple examples of parse trees that are used in the study of grammar, and were developed by John Bacchus and Peter Nauer back in the 50s and 60s. These people originally were linguists thinking about, how the English language connects up together. And you guys probably remember doing grammatical trees back in middle school, or at least I do. I don't know, maybe you guys are younger than me and they don't make you do that anymore because, man, it was terrible. But let's do one. Oh, you know what? I haven't done this in a long time. Do people know what I'm talking about? Grammatical trees? Didn't make you do one. So here, let me show you an example here. So here's the young man caught the ball, right? There's a noun phrase, the young man. There's a verb phrase, caught the ball, right? And inside of a noun phrase, there's an article, adjective, and noun. The verb phrase, there's the verb, and then the noun phrase, the ball, right? So you can kind of take the sentence and break it up into these pieces, right? Yeah, so back in middle school, I used to have to do these. I'm glad you guys don't have to do it. That's nice. It's not that fun. English class was never my forte. Spelling and grammar trees. Woof. But that study got translated into the study of computer languages, actually. And so the way that a compiler works is the same way, because there's a grammar to programming languages like C++ or Java or Python or any language, programming language, that works in the same way. And so when you write a computer program in Visual Studio or Xcode or something like that on the Linux server, and you compile it, part of the compilation process is parsing, right? So you actually take the code that you wrote and you break it up according to the rules of grammar for that programming language, which is an essential step. It's a necessary step to getting your code to work, right? So although these folks were studying grammar, that study was then used in the development of computer languages as well. And it's an essential part of compilation. So without these grammatical trees, we couldn't have computer programs, it turns out. The book gives another example talking about chemistry and the structure of hydrocarbons. And Arthur Cayley, who we're going to talk about a little later, was a British mathematician and among other things, chemist as well, obviously, studied these hydrocarbons and the structures that they made in terms of graph theory. That webwork problem that we saw when we started up, Cayley's formula is from that same guy, Arthur Cayley. So there's a lot of crossover into different disciplines with the idea of trees, right? So maybe we should do a little bit more vocabulary here. So there are two kinds of vertices in a tree. Can anyone name the two kinds of vertices and what they mean, what they are? Terminal and internal, very good, right? So two types of vertices. Right? There's terminal, which is also called a leaf, and internal, which is also called a branch. And it's really easy to tell these two kinds of vertices apart. Let's do this. Do some highlighting here. So the terminal vertices, those are these ones. Right? And then the internal vertices, those are these ones. How can you tell the difference? It's a really simple property you can use to distinguish those two different kinds. Good, the number of connections or degree, that's exactly right. So the terminal vertices have degree 1. And internal vertices have degree strictly larger than 1. Could be, two or more, right? So for example, this vertex has degree 2 right here, but this one has degree 4, right? And this one has degree 3, and this one, oh, that's not, I colored that one wrong. That has degree 2, that should have been internal, sorry. There we go, that's better. Right? Okay, any questions about that? Does that all sound okay? Okay, cool. So I'd like to circle back to what we were talking about before with how to mess up a tree, right? Now I said that if you add an edge inside of a tree, it's gonna screw it up. It's gonna make a circuit, right? And it doesn't matter if I put the edge between two internal vertices or two terminal vertices or internal to terminal, doesn't make any difference, right? No matter where I add an edge in here, right, it's going to ruin the tree property, which is that it's circuit free, right? But that says something pretty interesting about the edges, right? If we add just one, right, then we don't have a tree anymore. Well, what if we remove an edge? What happens then? Let's say we had, forget about the rest of them, we just have a single tree and we remove an edge. What happens in that case? Yeah, it disconnects the graph. It turns it from a tree into a forest, right? So if we have just a regular old tree, if we add an edge, that makes it not a tree because we make a circuit. If we get rid of an edge, that makes it not a tree because it makes it a forest, right? So there's something very specific about the number of edges that we have here, right? If there's one too many, it doesn't work. If there's one too few, it doesn't work, right? So there's something really specific about the number of edges that we have here. And what relationship is that? What is the relationship between the graph being a tree and its number of edges? It is, well, it doesn't have to be odd, right? Because I could have, let me give you a counter example here. So this is a tree with an even number of edges, right? Oh, okay, so Sean and Kobe, you guys got it. It's the number of vertices, and so your book calls the number of vertices n in graphs, right? So here n would be equal to 2. Sorry, pardon me, n is equal to 3, the number of vertices, right? And the number of edges is always the number of vertices minus 1, right? And we can see that here as well. So let's do a count. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 vertices. Let's count the edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there you go, 10 and 11. On this example here, we've got 1, 2, 3, 4, 5, 6, 7 edges, and 1, 2, 3, 4, 5, 6, 7, 8 vertices. So that relationship holds. And of course, here we have 2 and 3. Right? And the size of the edge set equals 2. Right? And let's just, for notation's sake, we'll say the size of the vertex set, we'll just call that n, just so I don't have to write so many pen strokes, right? Laziness, efficiency, right, as always, right? And so we should be able to prove this, right? Because it seems like a pretty common pattern. It's true for all these random goofy trees we wrote down. So let's prove it, right? So how could I prove that the number of edges in a tree is equal to the number of vertices minus 1? Any thoughts on that? By contradiction? Okay, say more, David. How do you mean? Okay, there's a tree that has more edges than vertices. Okay, or even an equal number of edges and vertices. And there's a tree with more vertices than edges. I guess you mean more vertices than n minus 1 edges. Prove that both raise contradictions. Okay, well, we could do that, but I think there's a little bit cleaner way of doing it, right? So instead of proof by contradiction, what's another proof strategy that might be good here? Sean says the book does induction. So I think induction is kind of a nicer way to do this, and it's not well, I mean, it is an induction proof, but it's not quite so formal as the ones that we did last term, because we're just drawing pictures here, so that's kind of nice. Really, what we mean by an induction proof is building a tree, right? And Lucas, that's what you're saying. Yeah, that's right. So we create a tree by adding vertices and show that the edges always equal n minus 1, right? So we will maintain the sort of style for an induction proof of doing a base case and an inductive case. So let's prove that in a tree, the size of the edge set equals the size of the vertex set minus 1, right? So if we do a proof, what would our base case be? One vertex, right? The trivial tree, the seed, as we said, right? So for a tree with the size of the vertex set equals 1, there can be no edge. So the size of the edge set equals 0. Why can't there be an edge if we just have a single vertex and we want to have a tree? Let's just go through that verbally. So we have this guy, right? One vertex. If we wanted to put in an edge, why would that not be allowed? I guess, so David, here's where that proof by contradiction is going to kind of come into play. Yeah, the only possible edge would have to start and stop at that same vertex because that's the only one available, right? And if we did that, we would put in a loop, which means that it wouldn't be circuit free anymore, right? So that style of the base case is a bit of a proof by contradiction, I think. Does that sound good? People happy with that? Makes sense. Okay, great. So then let's try the inductive case. Right? So let's say that we start with a tree. You know, I'll make up sort of a, you know, a simple little tree here. Okay, so here's a tree. Could be any tree you want, right? Now, what are we doing induction on? What's our sort of n+1 situation? Add one more vertex, right? So we're doing induction on the number of vertices, right? So if we increase the number of vertices, okay, so let's add a new vertex right here, right? Well, if we add a new vertex, what do we know? We have to connect it for it to stay a tree, right? So we have to add at least one edge to keep the graph connected, right? We must add at least one edge to connect that new vertex to the tree. Does it matter where we connect the other side of the edge to? Can we ruin the tree property by connecting it to this one instead of this one, or this one instead of this one? Does it make any difference? Is there a way that we could connect up this vertex and create a circuit and ruin the tree? No, there isn't, right? It turns out we could connect this to any one of the original vertices here. Doesn't matter, right? Any one of these we could connect and no circuit's going to be made, right? Does everyone see that? I mean, let's pick one. So if we just connect it up right here, right? Then of course there's no circuit. It's just, taking a new path, but it's not circling back around anywhere. Or if I added it over here to this one, well, that'd be fine. I haven't connected up to any of the others, right? So one edge to connect the new vert to the tree at any previous vertex, or I'll say any existing vertex. Okay, so we know that we have to add at least one edge. What do you think the second part of this is going to be? At most one edge. Very nice, right? You're getting the lingo down. Good. So why can we add at most one edge for each vertex? Because otherwise we would make a circuit, right? Okay, so if we add more than one edge, a circuit will be formed. Okay, now let's think about that for a minute. Okay, so why would that be? So I've kind of ruined this with all the lines. Let me do another example. So I've got a tree here. Okay, there's a tree, right? And I want to add a vertex here. Which vertex should I connect the new one to? Any of them, but let's pick one. Which one do you like? The rightmost. Okay, sure. There we go. Okay, so we're connected down there. We've got our new vertex and we've added one edge. Now, why would it be that if we add another edge, we'll make a circuit? So Lucas, that's right, but why? If we add an edge to something that's already a tree, then we'll ruin it. But why would that be? Like, how would we prove that? How could we prove that a circuit will be formed if we add an extra edge to the tree? Ideas? Yeah, I think that's a great explanation, Lucas. Every vertex is connected to every other vertex because we have a connected graph, right? So there's a way to get from every vertex to every other vertex. In other words, there exists a walk between every pair of vertices. So pick any pair of vertices, this one and this one. Let's say, okay, there's a walk to get between these two. You go that way and that way, right? And you can do that for any pair, between this one and this one, right? There's a walk to get between those. You go boom, 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 these four, right? Okay, so because the graph is connected, there exists a walk between every pair of vertices. People good so far? So let's write that down. Let's come over here, right? This is because there exists a walk between every pair of vertices. Since the graph is connected. Okay, good. So if we add another edge, right? So if an additional edge is added, between any pair of vertices, right? Doesn't matter which pair, right? Right? Then what's going to happen? There's a second connection, or I would say a distinct walk, a new kind of walk between those two vertices. So for example, let's say we're going from this one to this one, right? And I want to add a new edge right there, right? Well, there's already one walk between these two vertices, and now I've created a second distinct, a different walk between these two vertices, right? So if an additional edge is added between any pair of vertices, a new walk between those vertices is created, right? Okay, so how does that mean there's a circuit then? Why would it be that if we have two different walks between a pair of vertices that means there's a circuit? By definition of a circuit, it stays connected if you remove an edge. Okay, yeah, so let's look at the definition of circuit. So let's pop back to that here. Where's our definition of circuit? Well, it says a circuit is a closed walk that contains at least one edge and does not contain a repeated edge, where a closed walk is a walk that starts and ends at the same vertex. So the definition of a circuit, keep in mind here, let me throw this over here so you can read it. So a circuit is a closed walk, which means a walk that starts and ends at the same vertex that contains at least one edge and does not contain a repeated edge. So that the definition of a circuit does not say that it stays connected if you remove an edge. I think that's something we would have to argue or prove or justify in some way, right? So how could we argue that? How could we say, well, really what we want to do is sort of redefine a circuit, which I think is what you were going for there, David, which is the right move, which is to say, a circuit is a walk. Well, a circuit is, consists of two different walks between two vertices is sort of what we're going for here, right? But how can we describe that, or how can we explain that? And I'm sorry, and you had another little part here. It says it stays connected if you remove an edge. Well, that's true, right? So if we have a circuit and we take an edge out, then everything is still connected, right? So here, I'll pop up here. So if I have a circuit like this, so there's a circuit, right? Everything's all connected here. And if I remove an edge, any edge, doesn't matter which one, I'll remove this one, right? Then everything is still connected up, right? There's still a walk between any pair of vertices, even if we remove one edge. So is that how we should define a circuit then? It stays connected if you remove an edge? Okay, so Lucas, you're saying one walk goes from A to B, the other goes from B to A, and you can combine them to make a walk from A to B back to A. Ah, so that's clever. I like that. It's like transitivity almost, right? You have A to B, and if you put in B to A, right, a distinct walk, then you can combine those transitively to get from A to B back to A, which is a circuit. That's really elegant. I like that a lot, right? So we'll say, you know, the first walk goes A to B, and the new walk, sort of vert A to vert B. These are both vertices, right? And the new walk goes B to A through a different path, right? By a different path. Combining these, we get a walk A to B to A, which is a circuit. Cool. What do you guys think? Does that make sense? That walk wouldn't necessarily contain a repeated edge, no, because so take this one for example. Let's just never mind. Okay, and let me go through it anyway, right? So let's think about, it doesn't even have to be, you know, vertices that are connected by the new edge, right? The new edge doesn't even have to be involved in the new walks that we're considering. Let's call this one A and call this one B, right? So before, there was one walk from A to B. Maybe I'll call this one C, D, and E, right? So before, the only walk from A to B was A, C, B, right? But now there's another walk from A to B, which is A, D, E, B, if I add this new edge, right? And so what I could do is I could take walk number one, combine it with the reverse of walk two, so that I get A, C, B, E, D, A. Got to go in reverse order, right? So I go A, C, B, E, D, A, and there's my new circuit I've made, which is, of course, not allowed, right? What do you guys think? Does that look good? Cool. Yeah, very nice. Very nice, David. We agree. All right, cool. So there's my proof. Every tree has exactly n minus one edges no matter what. Well, what about a forest? How many edges does a forest have? Here's a little addendum. Oh yeah, they're definitely infinite graphs. There's a whole study of them. It's yeah, that's a whole thing. It could be a tree with infinite vertices that the induction never gets to. Well, yeah, I mean, if you're going to talk about a graph with infinite vertices, then you're going to want to be careful thinking about paths, because if you're talking about finite paths in an infinite graph, that's going to be a really different study than talking about infinite paths in infinite graphs, right? So your question is, could there be a tree with infinite vertices that the induction never gets to? Well, I guess I see what you're saying, right? Because earlier we said infinity minus one is still infinity. Is that what you're getting at? So that you're trying to sort of argue with this formula by making both of these equal to infinity? Is that what you're getting at? Not really. Can you explain one more time then? If induction gets to every graph, if there can be graphs with n equal infinity. Well, so let me see if I can phrase this right. You're asking if there, okay, so maybe there are multiple questions here. First of all, you're asking if there are graphs with infinite vertices, and the answer is yes. Well, there's two questions there. Do people think about the idea of graphs with infinite vertices? Yes. Do there exist actual representations in the physical universe of graphs with infinite vertices? I don't know. Depends on if the universe is infinite or not. So there's two different questions. Does it exist in reality, or do people think about it? And I don't know if it exists in reality, but people definitely think about it. There's a whole discipline of infinite graph theory, right? So that's the first question, right? But I think that, but what you're asking is, does this proof apply to graphs with infinite vertices? Because maybe the inductive case never reaches infinity. Is that what you're asking? Yes. Okay. And I think the answer is no. This proof doesn't get there. I think you could think about a circuit-free infinite graph, and that's fine, right? But I think at the point when you have an infinite graph, trying to equate the number of edges and the number of vertices according to some formula, or I guess I should say relate them to, because it's one is the other minus one, right? Sort of ceases to make sense, right? Because as we've already shown, infinity equals infinity minus one, right? So sort of subtracting one off of infinity doesn't really do anything, right? In some sense, it doesn't really mean anything to take one away from infinity, right? So I think in the case of an infinite graph, this relationship would break down, right? Because infinity minus one is equal to infinity plus one, right? But they're both equal to infinity, so it doesn't really make any difference if you add one or subtract one. So this relationship doesn't really mean anything in that particular case, right? So I think I would be comfortable with your interpretation of this breakdown of meaning by saying that the inductive case never gets there. I think that's a fair way of putting it. That's not how I would put it. I would say the relationship is meaningless. And the reason why has to do with infinity rather than with the way that we were trying to get there, if that makes sense. but I think we're saying the same thing. I think that's too subtle of a point to really even mean that much. I think we're saying the same thing. Does that answer your question then, Lucas? Yeah, it does. Perfect. Yeah, I think that there's a lot of things you can talk about in infinite graphs, and the number of edges is not one of them, right? Um, you could think, excuse me, I think you could, think more productively about something like the average vertex degree in an infinite graph, and that would still mean something, right? Because all of the vertices will have finite, well, I get they could at least all have finite degree in an infinite graph, right? And so long as you're thinking about something that can be quantified, numerically in a finite way, then it still makes sense to talk about. So you could think about an infinite graph with different average vertex degree, and then maybe ask the question, you know, um, how far is the average walk between two randomly chosen vertices, given, a certain amount of average vertex degree, right? And maybe something, and infinite graph theory is not my area of study. I've never studied it, but just to spitball for a second, right? Let's think of, if you had this infinite graph, okay, infinite vertices, right, and infinite edges, maybe you could say, well, if there's edges that connect vertices from way over on the other side of this infinite universe, right? Maybe you could describe something about the average length of the shortest path between two vertices as being in some way related to the average degree of the vertices in that infinite graph. And maybe you could get some finite numbers out for that if if you could do some sort of convergent sum or something like this, where you find the limit of some convergent sum, and maybe that sum converges if you build your graph in just the right way. And even though it's an infinite graph, you could have finite walks between some of the points on the infinite graph. Probably not all of them. If it's infinite, then probably some of the paths between them would be infinite, but maybe some of them would be finite, and you could study which ones were finite, which ones were infinite, how long they are, how it relates to the average vertex degree, stuff like that, right? In essence, what I'm trying to do here is I'm trying to think of properties of the graph that would still be finite, because at the point when you're talking about objects of infinite size, it kind of becomes meaningless in a pretty pretty obvious way, right? So you can make some things infinite and other things are still finite, and I think that's kind of the game that you're playing. Does that make sense? Yeah, mostly. Okay, that's me spitballing. So I'm glad it mostly made sense. That's the most I can hope for. Okay, no, that's a great question. Yeah, if you're interested in infinite graph theory, I highly recommend. I'm sure that's very fascinating. But let's go a little bit different way. Right. So what I'm curious about is a little postscript here. Right. The number of edges in a forest is what? Okay, so Sean, you're saying something like n minus k, where k is the number of disconnected parts. Yeah, I agree completely. It depends on the number of components. So let's do an example, right? So let's say we have, a little forest up here. I guess I've kind of run out of room. Well, I'll just do it down here. So here's my little forest. I've got, this guy. I've got single vertex. I've got this little binary tree. That's a good forest. We'll start with that, right? So let's count the number of vertices and the number of edges and see if we can come out with a formula. So we've got vertices 3 plus 1 plus 7, which makes 11, right? So we have the vertex set size is 11. The edge set, how many do we have there? 1, 2, 3, 4, 5, 6, 7, 8. So I think, Sean, your formula looked to be correct, right? Where the number of edges in a forest is the size of the vertex set minus the number of components. Yeah, each component has n minus 1 edges, and the minus 1s will all add together, right? Minus 1, minus 2, minus 3. So minus the total number of components. I think another good way of thinking about that is that a tree has one component. So a single tree follows this rule too, right? The number of vertices minus the number of components. Well, we have one component, so the number of edges is v minus 1, right? Does that make sense? Makes sense. Cool. Yeah, this is what I would call a generalization of our original formula, right? Because a more general situation than having one tree is having many trees, right? A tree is a forest, right? It's a one tree forest, right? It's not a very big forest. It's not a very good forest, but it's a forest nonetheless, right? It's kind of, it's what I would call the trivial forest, right? A forest with a single tree. But if you generalize out to a multi-tree forest, right, it turns out that this formula still applies to the more specific case of just having that single tree, right? And a huge part of the development of the ideas in mathematics is about thinking of a specific problem, then generalizing that problem to something like, oh, well, I don't know how to do it for one tree, but what if I have multiple trees, right? Solving the general problem and then using the formula you got from the general problem to solve the specific one. It's actually a really common strategy because it doesn't always work, but a lot of the time, some of the time, you know, if you move from a specific problem to a general problem, the general problem is easier, right, than the specific one. So that's, you know, that is a common sort of strategy in math, is to say, oh, well, you know, this specific problem is really hard. What if I think of a more general problem, solve that, and then use that solution to go back to my specific problem to solve it, right? So I did want you to alert you to that sort of strategy because it is a common one. Any questions there? Does that sound good? Okay, cool. So our next little proof here is going to be along similar lines. And it says, if G is a connected graph, so if G is connected and C is a circuit subgraph of G, which means C is just a circuit that lives inside the graph G somewhere, right? Then any edge can be removed from C and G will remain connected. So this is really closely related to our last proof, right? So what do you guys think about this? How could we argue this? Yeah, similar to what Lucas said above. Okay, so would you say it again for me? How would that work? This is a little different, right? Because now we're not talking about a tree, right? We're talking about just a graph in general. Yeah. So it's similar, but it's not exactly the same. So how would you argue it? Okay, because C is a circuit, and there's more than there's at least two ways, so greater than or equal to two ways to connect any two vertices on that circuit. If we remove one edge, there's still one way to connect A to B. Okay, perfect. So let's just be careful about our labeling here, because I think that's going to be really the hardest part, is just labeling everything. Okay, so let's say let A and B be any arbitrary pair of vertices in the circuit C, right? So by definition of a circuit, or I'll just say since we have a circuit, since A and B are in the circuit, there are two different paths between them. And I think you can see that pretty easily with a picture. If I have a circuit, okay, here's A, here's B, right? So here's path number one, and here's path number two, right? Cool. So if we remove one edge, let's say there's an edge right here that we get rid of, right? If we remove a path, or pardon me, if we remove an edge, if an edge is removed, there is still a path between A and B, just going the other way around the circuit, right? And since every pair of vertices have a path, right? Since there is still a path between every pair of vertices, the graph is still connected. All right. What do you guys think? Does that make sense? Questions? Okay, so just for a little comparison, let me show you how your book did it, because it's a lot more specific and a lot more complex. Okay, now the way that we did it is fine. I would be happy to accept this as the answer to one of your homework proofs, the collaborative proof or the graded proof, something like that. This would be a perfect answer. I think that'd be great. It's logical. It makes sense. Everything's labeled, and I think the proof has really been achieved here. But your book does use a pretty different style, and I did want to show that to you, right? So here goes. Okay. So here's our situation. Here's our circuit, right? And we're going to have a graph that sort of has additional junk on there, right? So there's these other little arms coming off of our circuit, right? But here's what it says. Okay, so G is a connected graph, C is a circuit in G, and E is an edge of the circuit. Okay, we're going to form a subgraph G prime by removing the edge from G. Okay, so the vertex set of G prime is the same as the original graph, but the edge set of G prime is the original edge set minus this specific edge called E that we removed. And we have to show that the new graph G prime is still connected, right? And to do that, we must show that if U and W are any vertices of the graph, any two that you want, then there exists a walk between them, okay? So we'll suppose U and W are two vertices of the new graph with the edge removed. Since the vertex set are the same, the vertices are still there, so we don't have to worry about one of the vertices vanishing. They're all still present, right? And there's two cases, okay? So E is not an edge of W, where W is the walk between those two vertices. So they've gone a bit farther, right? We didn't label the old graph and the new graph with the edge missing. We didn't label the walk at all as W. We just labeled the two vertices. We called them A and B. They're calling them U and W, right? So they're labeling a bunch more stuff. They're labeling this new graph. They've defined it precisely, and they've labeled this walk W, okay? Now, if the walk is not, E is not an edge inside the walk, then the walk is still there. So that's pretty easy, right? If, if, for example, my walk was from here to here, right, between U and if this guy was W, well, then the walk's the same. We can still do that. So we're good. What if we had, U and W here, and we said the walk between them goes this way, down along the bottom, and we remove this one on top? Okay, well then again, the walk stays the same. The edge that we removed has nothing to do with the walk, and it's still there, right? But if the edge that we removed is in the walk, now we're going to show that you can go around the other way, right? Instead of going down around the bottom of this hexagon, you could go around the top side, which is what we were getting at with our idea here, right? Where instead of going around the top, well, if that's messed up, then you go around the bottom. That's the basic idea still. They're just being really specific with the labeling, right? So if E is an edge of the walk, then the walk must include a section of the circuit because the edge that we removed had to be from that circuit. So we'll define the circuit, V0, E1, V1, E2, a sequence of vertices and edges that circles back to V0, right? And E is one of the edges of the circuit. So we'll say E equals EK, so the kth edge in the circuit. Then the walk contains one of these two sequences, right? We either have E sub k going from k minus 1 to k, or the other direction. So we're either sort of going clockwise here or counterclockwise here, sort of backward, right? So if W is this kind of a situation and it's going clockwise, well, then we'll just take the counterclockwise walk. right? Or in the other situation, if W contains the clockwise direction with the edge in it, then we'll take, sorry, the counterclockwise direction with the edge in it, then we'll take the clockwise walk, the other one, right? Which is a really long-winded way of just saying, go the other way around the circuit, right? But I did want to show you sort of the extent of the precision in the notation that the book has used, just for a difference in style, right? So our style was a lot more sort of free form and English based than your book style, which was much more formal and labeled everything, the walk and the circuit and the edges and the edge removed and all the vertices are all labeled. You can do that and that's fine, or you could do it this way and this is fine. I prefer this way. I think that that this is still proves it and is easier to understand, which to me that's a win, right? What do you guys think? Do you prefer this style or the style in the book? You prefer the English style? I would call it the English style and the formal style. Okay, so it looks like at least Kobe and Natasha prefer the English style, and I do too. I think it's the trap here, right? The pit that you can fall into is if you do this sort of less formal style and you miss something, right? Because what the formalism does is it ensures that you haven't made a mistake, right? Because if everything is, an algebraic, you're just doing logic and algebra the whole time, and following an algebraic rule for every little line of the proof that you do, then it's impossible to make a mistake, right? And here with this English description, well, you can make mistakes there because it's not as precise, right? So that would be sort of the downfall of this style, is that like you might make a mistake if you do it this way. But in this case, we haven't. So that's good, right? Okay, so let's do one more, and that'll finish up section 10.5. So our last one if G is a connected graph with the vertex set size equal to edge set size minus 1. Oh, I guess I should say edge set plus 1. Oh, wait, did I do that wrong the whole time? Uh-oh. Oh, boy. Now I'm worried. Oh, no, I just did it the other way the last time. Okay, sorry. I just went backward. Sorry about that. Edge set equals the size of the vertex set minus 1. That's better. Then G is a tree. So this time we're proving the other direction. Before we said, hey, if G is a tree, then the edge set equals a vertex set minus 1. Now we're going the other way. We're saying, hey, we've got a connected graph, edge set equals vertex set minus 1, then that has to be a tree, right? So we're just proving the converse, right? So now we have sort of an if and only if after we prove this, right? We'll say G is a tree if and only if the size of the edge set is the vertex set minus 1, proving both directions, right? Any questions about that? You see how I proved the implication and the converse in order to get that biconditional if and only if. Does that make sense? Sure. So before I was saying, before I said G, the tree, implies the edge set equals the vertex set minus 1. And now I'm saying the edge set equals the vertex set minus 1 implies G is a tree, right? And now I get both directions, so I get that. Oh, you got it. Okay, cool. So since now I have both directions, I can just do if and only if, right? And which is, you know, a stronger statement, right? A more, you know, I can say more that way, right? Both directions of the implication. Okay, so what do you guys think? How could I prove this? Any ideas? By contradiction. Okay, so what kind of contradiction would we like to set up? Assume it has a circuit and show there aren't enough edges. Great. Okay, so let's assume for contradiction that G is connected where size of the edge set is not equal to the size of the vertex set minus 1, but G is still a tree. Well, I think we're going to have to go sort of two ways with this, right? I think we're going to have to consider the case where we have too many edges and too few edges, right? Do we have to do that? Maybe we don't have to do that. What do you guys think? Do we have to do, too many edges and too few edges, or just too few? Just too few. Okay, why is that? Not sure. Okay, that's all right. Other ideas? Because it's a connected graph. Well, what does that have to do with it, David? So I see that earlier, Sean had a good idea earlier about the too few part of it, which is that if we make a circuit, there won't be enough edges left to connect everything, which is absolutely the right idea for too few, right? So David, if that's what you were going for, then I agree with you. That's part of the proof. But what I was asking is, do we need to do two cases where we assume, first of all, that the edge set is greater than the vertex set minus 1, right? And then a second case where the edge set is less than the vertex set minus 1. Do we need to do both of those, or can we get away with just doing one of them? Okay, so Sean, you have an idea. So you say we should do both, and you have an idea for the too many, which is this first one. You would show if there's more than one n minus one edges, there must be a circuit, so it's not a tree. Okay, and how do you know that?
So I'm thinking about like the case where you just have like a chain of nodes.
Okay,
If there are even just n edges in a chain of n nodes, then the last node must connect to one of the other nodes, and then there's some kind of circuit.
sure. So you're talking about this situation.
Yeah, if there's another edge dangling off the end there so that there's n edges, it's got to connect to something, and if it's one of those other nodes,
It's got to
then
connect back to one of these guys, right?
it's got one of them, yeah, because an
Which would make a
edge
circuit.
has to have two vertices, right?
Yep, absolutely. So that takes care of, this is called a line graph for obvious reasons, right? So that takes care of a line graph. I agree with you there. What about a tree more generally? Why would it be that if we increase the edges past the number of vertices minus one in any graph, we're not going to get a tree to pop out? First proof covered it by construction. Yeah, I think that's right. Like, so we said, you know, with our inductive case over here, right? If we increase the number of vertices, we have to add one edge to connect each new vertex to the tree, right? So in this situation, right, I think what we're saying is, okay, well, we've got, let's maybe think through it with an example. Maybe that would help, right? So this line graph works fine, I think, for our example. So we could say, okay, well, we've got our connected graph. We've got the number of edges is bigger than the number of vertices, right? Well, in that case, what's going to happen is that last edge that we put in has to make a circuit because it has to connect two vertices that already have a path between them, right? Does that make sense? So once the size of the edge set equals the size of the vertex set minus one, there is a path between every pair of nodes, every pair of verts. Therefore, adding more edges must create a circuit. Okay, well, why would it be that once we get up to the number of vertices minus one for the edges, there's a path between every pair of vertices? Well, I think, David, your comment there is right. Our first proof covered this thing, this part, this sentence, by construction, right? Because what we said was, well, we start off with the single vertex and no edges, right? And for each additional vertex that we add one more edge. And it doesn't have to be in a line. It could be, you know, going off sideways and stuff. That's fine. But for each new vertex that we add, you know, we have to connect it back up somewhere with some new edge to keep it connected, right? And so once we get up to v minus one edges, right, then there's a path between every two vertices because that's the sort of the construction that we use to build our connected graph in the first place, right? What do you guys think? Do people have questions about that? Does that make sense? Should I say it one more time? Okay, well, there's a lot of silence. So let me say it one more time. Okay. In order to build a connected graph, adding one vertex at a time, what we'll need to do is connect that vertex to some other vertex in the graph via an edge, right? So as we build this graph, keeping it connected one vertex at a time, for each vertex that we add, we have to connect it back to something, right? Doing that will cause us to have the number of edges equal to the number of vertices minus 1, according to the construction in our last proof. And so if we add any additional edges than that, a circuit will be created, right? Because there's already a path between every pair of vertices by our construction, just because it's connected, right? That's what connected means. Does that make sense? Did that help? Yes. Okay, cool. Excellent. So let's do the second part, right? Where the number of edges is less than the number of vertices minus 1. Well, in that case, I'd like to go with, let's see, who was it here? Sean's suggestion, right? So let's say that we have a tree. Well, let's do it this way. Let's say we have a bunch of vertices. Let's say we have, I'll just do it like this. Okay, we have a bunch of vertices, okay? 7 of them, right? And we want to add a number of edges that's less than 6 of them, right? So if we add 6 edges, of course, then we can make a tree, and that's fine. But we want to add less than 6 of them. Okay. Well, what's going to happen there? Yeah, we won't be connected. If we only add 5 edges, 1, 2, 3, 4, 5, right? There aren't enough edges to connect everything. So in this case, there are not enough edges to connect everything. And these are contradictions, by the way. So that's a contradiction. Adding any more edges must create a circuit. That's a contradiction. There are not enough edges for everything to be connected. That's a contradiction. And we actually have one more case to consider, that the size of the edge set is equal to the size of the vertex set minus 1, but there's a circuit. And that's really what Sean, I think, was getting at, right? So in that case, we have, again, let's do our 7 vertices. Oh, no, that's more than 7. Sorry, I did 10 this time. That's okay. So I did 10 vertices, right? And I add in the right number of edges, but there's a circuit. So I'll add in 9 edges. 1, 2, 3, 4, 5, 6, 7, 8. And when I do that 9th one, right, if I want to make a circuit on the 9th one, let's say I do this, right? Well, that's going to leave out one of my vertices, right? So building a circuit with one of the edges, one or more, right, of the edges means what? So what do you guys think? What's going to happen if we build a circuit with one or more of the edges? You'll have a disconnected graph, not a tree. Yeah, there will be at least one of the vertices not connected up to the tree, right? So building a circuit with one of the edges will leave out or will leave disconnected one, we'll leave at least one of the vertices disconnected because we ran out of edges, right? Yeah? What do you guys think? Yeah, the pictures are helpful, right? That's what I like so much about graph theory, because I'm a very visual person. The formulas and algebraic derivations are not the way that, I mean, I can do it, but that's not my forte mentally. It's not my strong suit. And for me, it's pictures and visual stuff. So I really like graph theory for that reason, because you sort of draw pictures to understand what's going on, and that always helps me. So hopefully that's helpful for you too. Do directed trees have any additional rules? Yes. So we're going to talk about directed trees in the second part today when we talk about Cayley's formula. And it turns out that you can count how many different trees there are of a specific size. And you can do that with directed trees with a really nice proof. But for undirected trees, these are all undirected trees that we've been talking about the whole day so far. It turns out you can't do that same proof with undirected trees. So if you want to know how many different trees there are, it's a lot easier to count them if they're directed rather than undirected like these ones. Yeah. Cool. Okay. Other questions? Okay, sounds good. Well, we're halfway through, so why don't we take 10 minutes, go get a snack, get a drink of water, some coffee or whatever, and we'll come back and we'll jump into section 10.6. See you guys soon. All right, so I want to do some of these practice problems from section 10.5. And the idea is to either say that this graph doesn't exist, or if it does exist, then draw a picture of it. So if people want to share screens and use paint or just sort of describe it, we'll sort of figure it out as we go. So here goes. So a tree with 9 vertices and 9 edges. Does that exist? No. Very good. Because of the thing that we just proved, the rule. There has to be one less edge than vertices. Okay, how about a connected graph with 9 vertices and 9 edges? Does that exist? Yeah, we just put a circuit in it. Very good, right? So we'll have, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the ninth edge, right? Cool. Okay. How about a circuit-free graph with 9 vertices and 6 edges? Yes, we can. Okay, so what's that going to look? Yeah, disconnected, right? So graph circuit free, 9 vertices, 6 edges. Well, let's just count the number of edges. So we'll do 1 edge, 2, 3, 4, 5, 6, which gives me 7 vertices. And there's 2 more vertices just hanging out, right? So that's a graph that's circuit free with 9 vertices and 6 edges. Okay, how about a tree with 6 vertices and total degree 14? Does that work? So let me say it one more time. It's a tree, 6 vertices, and the total degree of the graph is 14. No. Why not? Yeah, because if the degree is 14, that would make 7 edges, because each edge contributes 2 to the total degree, which would make 7 edges and 6 vertices, which is 2 too many, right? If we had 6 vertices, we'd have to have 5 edges, not 7. Very nice. Okay, how about a tree with 5 vertices and total degree 8? Yes, right? That's just a regular old tree. So 5 vertices, total degree 8. 1, 2, 3, 4, 5. Okay, and let's count the total degree. 1, 2, 3, 4, 5, 6, 7, 8. So there you go. Cool. How about this one? A connected graph with 6 vertices, 5 edges, and a circuit. So connected graph, 6 vertices, 5 edges, and a circuit. Yes. Okay, so what's it going to look like, David? Triangle and 2 lines. Oh, it has to be a connected graph. A connected graph, 6 vertices, 5 edges, and a circuit. So it does have to be connected. The 2 lines off the triangle. Okay, so I see. I thought you meant separate. So we got a triangle with 2 lines like this. Is that what you're talking about? All right, so we got a graph. It is connected. It has 6 vertices, 1, 2, 3, 4, 5. Oop, nope, we're missing a vertex here. That's only 5 vertices. So change your mind, or can we fix this? Change your mind. Okay, so if we add that 6th vertex, what we'd have to do is take one of those edges away and reorient it over here to keep everything connected, but that's going to kill our circuit, right? So that one would be in contradiction to this proof, right? If we have the number of edges is 1 less than the number of vertices on a connected graph, it has to be a tree, which means it can't have a circuit. Nice. Okay, good. So we got there. Awesome. All right. How about a graph with 2 vertices and 1 edge, but it's not a tree? Actually, we can do this one. Yeah, a loop and disconnected. Very good. So here's two vertices, one edge, not a tree. So if that was a simple graph with two vertices and one edge, then that would make it a tree. Or if it was a connected graph with two vertices and one edge, that would be a tree. But if we don't specify that it's simple or connected, then we can do this sort of cheating right here, right? Okay. How about this one? A circuit-free graph with 7 vertices and 4 edges. Sure, right? So how would you do that one, David? So one more time, that was circuit-free, 7 vertices, 4 edges. Yep, just a line with 2 disconnected. So 1, 2, 3, 4, 5, and 2 more, right? Okay, good. How about a tree with 12 vertices and 15 edges? So a tree with 12 vertices and 15 edges? Nope, that's right, too many edges, right? So I think you get the idea, right? Any questions on all that? Does that look okay? No questions? Okay, cool. In that case, let's jump into 10.6. So I'm going to start with a bunch of vocabulary, okay? And 10.6 is all about rooted trees. So a tree with a root, which if you've taken CS 260, you'll know is a really important part of data structures talking about binary trees, which is what we're going to be talking about in a minute here, right? So, but first, in general, a rooted tree is a tree in which one vertex is distinguished from the others, called the root. The level of a vertex is the number of edges between it and the root. The height of the tree is the maximum level of any vertex. Given the root and an internal vertex, the children of V are those vertices that are adjacent to V and one level farther from the root. Okay. If W is a child of V, V is called the parent of W. So you have a child, a parent on top and a child on the bottom of the tree, getting farther from the root. Two distinct vertices that are both children of the same parent are called siblings. If one vertex lies on a path from V to the root, then V is an ancestor, right? And if W lies on a root from, if W if there's a path from the root to W that passes through V, then W would be a descendant of V. And this will all make more sense with a picture. So let's check out the picture. There we go. All right. So here's our little picture. We've got our root. We've got the levels here, right? And you can sort of see it's all arranged vertically. And that's usually the way that rooted trees are drawn, with the root at the top and the leaves on the bottom. So it's kind of an upside down tree. Usually on a tree with, that grows in your yard, the roots are on the bottom and the leaves are on top, but this one is inverted, right? Roots on top, leaves on the bottom. Okay. Now the levels increase as you go down the tree, right? And now we have some little examples here, right? So V is the child of U. Get a better, oh boy. Get a better pointer here. Okay. V is the child of U. U is the parent of V. So you can sort of think of this like a family tree, right? Where it shows all your ancestors and grandparents and stuff on your family tree. You can think of it kind of that way, right? And the root, I guess, is Adam, right? Or some, monkey in Africa, depending on your persuasion, right? But someone from somewhere was the root of a humanity, and that would be the root of the tree, right? And then all the descendants are the people that are their progeny, right? So okay, so we've got V and W are the children of U. U is the parent of V and V and W are siblings because they have the same parent, right? If we called this one, Y, some other name here, right? This node here, Y would be the grandchild of U. Your book doesn't say that, but it's common terminology for talking about trees. And U would be the grandparent of Y. So this would be grandchild and grandparent, right? And of course, Y is a descendant of U, just like, you're a descendant of your grandparents, right? The difference between this and a family tree is that there's one node that produces lots of others. So this isn't really like a human family tree. It's more like an amoeba family tree where you have like one amoeba and it splits in half to make its two children, right? Rather than humans where, that have sexual reproduction rather than asexual reproduction, you'd have sort of two parents that would have a bunch of children coming off. Here we just have one parent that has children. So it's more like, amoebas that have asexual reproduction, that kind. So an amoeba's family tree, I suppose, right? So this thing is called a subtree because it's a part of the tree. And this subtree includes all the descendants of the vertex U. It's all the things that come underneath that are connected to it, right? And it says what have we not done yet? The height, right? So the height is the maximum level of any vertex in the tree. So what's the height of this tree? The maximum level of any vertex in the tree? Yep. So what number? 4. Yeah, exactly. Right. And so the height of the tree, another way to think about it, is the number of the largest number of edges that you can get away from the root, right? Which is 1, 2, 3, 4 edges, right? So that's just another way of thinking about it. And of course, the root, just like an array, the root starts at level 0, right? Just like an array starts with the 0th item, we have the root at level 0. So we start at level 0 rather than at level 1. And that does make a difference for some of the formulas that we're going to be looking at. So you do want to remember to start the root at level 0 rather than level 1. Okay, so let's do some questions. Maybe I should just do it this way. Okay, great. Consider the tree below, and let's answer some of the questions. So what's the level of V5 right here? 2, perfect. Okay, what's the level of V0? 0, nice. What is the height of this tree? 3, very good. What are the children of V3? 5 and V6, perfect, very good. What is the parent of V2? V0, good. What are the siblings of V8? 7 and 9, these guys, good. And what are the descendants of V3? 5, 6, and 10, very nice. So the descendants of V3 would be this subtree here, which include 5, 6, and 10. Let's do a couple more. What are the ancestors of V9? Four, 1, and 0, right? So from V9 going upward, these are the ancestors, right? V4, V1, V0. How many vertices are at level 2 in this tree? 3, very good. Because here's level 0, level 1, level 2. We've got 3 vertices on level 2. Nice. Okay. Any questions about all that? Does that look okay? Okay, cool. Moving right along. A binary tree is a rooted tree where each node has at most 2 children, could have less, it could have 1 child or no children, and each child is designated either the left child or the right child, right? Because you can have at most 2. So here's another little vocab exercise here. All right, so here we've got a binary tree because each vertex has at most 2 children. Okay, so here V is the left child of U, X is the right child of W. This is the right subtree of W. It's the part of the tree that's a descendant of W on the right. These are the descendants of W on the left. So that would be the left subtree of W. Any questions there? If there's 1 child, is it right or left? That's a great question. It depends. So you can see that there's actually both possibilities in this tree, right? Because right here, there's a single child of this node and it's a right child, but here there's a single child of this node and it's a left child. So it actually could go either way. Does that make sense, Lucas? Whichever you want. Yeah, some trees have a rule where if you only have 1 child, it's got to be a left child, or it's got to be a right child. But not with the trees that we're going to be looking at. And speaking of sort of getting away from the book's definitions and terminology, there's one more term here, which is a full binary tree, right? Is a binary tree in which each parent has exactly 2 children. Okay. Like in a binary search tree, it depends on whether the key is greater or less than the parent. Yes, that's right. But let's talk about full binary tree for a second. And let me give you an example. Is this a full binary tree where every parent has exactly 2 children? Yes, right? This is the only parent. These one, A and B, these are not parents, right? Because they don't have any children. So they don't matter. Every parent, it's the only thing that we're saying, every parent has 2 children. So this would be a full binary tree. What about this one? Would this be a full binary tree? No, why not? Which parent doesn't have 2 children? A doesn't have any children, but that's okay. It's not a parent, right? A full binary tree is only saying that every parent has 2 children. It's full, but not balanced, right? So this actually does count as a full binary tree. Now your book doesn't use this term, that I would use, and I believe WebWork uses it as well, which is a complete binary tree. Okay, so full and complete are two different things, right? Full just means, let me rephrase a full binary tree. No vertex can have one child, right? That's a full binary tree. You can't just have one node coming off of this guy. That's not allowed. You have to have either two or none. But a complete binary tree is defined a little bit differently, which is that every node on the same level has either no children or two children, right? Which then is violated by the A and the plus in this particular example, right? What do you guys think? Does that make sense? No DE, no children. Exactly. Perfect. Okay, so let me ask you this. Is this binary tree, there we go. Is this binary tree full or complete or neither or both? It is full, okay. Is it complete? Yeah, not complete, right? Because for complete, we would have to have two children coming off of each of C, D, and E, right? What do you guys think? Does that make sense? Cool. All right, and I believe that's the vocabulary that WebWork uses. If someone does see a contradiction there and I've got it wrong, please let me know, and I'll go through that with you guys. Oh boy. Okay. So your book was doing a little example here, example, where they were talking about parsing arithmetic expressions. Okay. Now, parsing, just in general, means splitting something up, right? So if if I've had one too many beers, then I might not be able to parse what my buddy is trying to tell me at the bar when there's background noise, right? So parsing just means dividing something up into meaningful components, okay? And we talked about parsing a little while ago with with the grammar, right? But in the same way that you can parse English grammar or the grammar of a programming language, you can also parse arithmetic expressions. So for example, they have this expression here, which is A divided by C plus D. And it turns out that you can make a binary tree to represent this. And that's that little tree that we were looking at before, where the internal nodes, remember internal means higher degree than 1, terminal means degree 1. So the internal nodes here are going to be operators, whereas the external nodes, or pardon me, the terminal nodes, which in this case are also called leaves in the case of a tree, those are going to be variable names. Right? So the internal nodes are operators, the leaves, which are the terminal nodes, those are the variables, right? You see how we divide A by the sum of C and D. You see the relationship here between the formula and the what's called the parse tree for that formula. Any questions there? I mean, just to be really pedantic about it, for each operator, the left subtree is all the things to the left of the operator. The right subtree is all the things to the right of that operator, right? So the left subtree of the division symbol is just A. The right subtree of the division symbol is C plus D, right? And then we sort of recurse downward into the plus to get the left and right subtrees of that. Does that all sound good? Questions? Okay, so let's do one more example. Got A minus B times C plus D over E. So I didn't put in all the parentheses, but let's just assume the usual order of operations. And let's build a tree, the parse tree, for this expression, right? So what's the root of this parse tree going to be? Let's build it, let's build it one step at a time. Not the minus. The minus is a bit further down. Yeah, the plus is going to be the root. Okay. What is going to be the left child and the right child of the plus operator? So let's do the left child first. Multiply. Good. What about the right child? Divide. Right? Because this is the first operation that we do. Here's the next layer of operations that we do, right? So that's the next level of the tree, is the next sort of layer of operations that we do in this expression, right? So let's talk about the multiplication. So in general, what's the left subtree of the multiplication going to look like? Not the left child, but the entire left subtree of the multiply. What's that going to be? A minus B, right? Where, of course, the operator is the internal node. The A and the B are the leaves. Okay, what about the right subtree of the multiply? C, very good. And how about the children of the divides? What are they going to be? I'm going to make them a little longer here. D and E. Very nice. Does everyone see how that works? Any questions? I'll let you think about it for a minute there. So operators will be parents and operands are children. Yep, exactly. Yep, that's right, Nathan. Yeah, good summary. Cool. Okay, so let's try a theorem. So we've got T is a full binary tree with K internal vertices. Okay. Sorry, let me do it this way. If T is a full binary tree with K internal vertices, then better. Then T has 2K plus 1, has K plus 1 internal, wait a minute. Oh, sorry. K plus 1 terminal vertices. There we go. And therefore, 2K plus 1 total verts. Right. So if it has K internal vertices and K plus 1 terminal vertices, then just adding those together gives us a total of 2K plus 1. Right? Is everybody happy with that? Any questions there? Okay, so let's do a couple examples. These examples we did up here. How many internal vertices does this tree have? the left tree here, how many internal vertices does that have? 2. And how many terminal vertices? Terminal vertices are the leaves. Yeah, 3, right? So it works, right? Because we have 2 internal, and then 2 plus 1 is 3 terminal, which is the leaves, okay? Here, how many internal vertices do we have in this tree? Yeah, for a full binary tree, right? Which is that every parent has 2 children. Now remember, the parent, in this case, if it has 2 children, that means it has to be internal, right? You see how that logic works, David? Yeah, nice. Okay, so how many internal vertices do we have here? Four. And how many terminal vertices? 5. Yep, so it works there too, right? We take the internal vertices, add 1, and we get the terminals, which is what we're saying here. And of course, the total then would be 2k plus 1, right? Because, we just add k and k plus 1. Here we'd have 9, 4 plus 5, right? Okay, so let's prove it. So what do you guys think? How do you think we can go about proving this? Induction. How would that work, David? Maybe I should ask you a simpler question. What would the base case be? How about that? Okay, 3-node full tree. Okay, so proof, so for induction, we have our base case, which is the root and 2 children, right? Here, internal equals 1, terminal equals 2. Check. Okay. So I'm with you there. So then what's the inductive case going to look like? So let's start with our base case. We're going to, induct on something. So what exactly are we inducting on? Well, let's build the bigger tree first. So what am I going to do to sort of build a bigger tree out of this guy? We have to add 2 nodes. Okay, so let me label these guys. Let's label them A, B, and C. Right, so where should we add 2 nodes, D and E? 2 children to one of the leaves. Let's add them to B, let's say. We call these D and E. Okay, so these are new, right? We're doing induction by turning a terminal node into a internal node, right? So for induction, we turn a terminal node, a terminal vertex with no children into an internal node with 2 children. In other words, we give 2 children to one of our terminal nodes, right? And that's what our induction is. And we have to have 2 children because it's got to be full, right? So every parent has to have 2 children. So if B becomes a parent, it's got to have 2 kids, not 1, right? Okay, so what does that do? How does that affect our count of the internal and terminal vertices? Adds 1 to each. Okay, why would that be? How does that work? So you're right, David, but it's a little bit subtle. So what's the tricky part? Okay, subtract 1 external, right? Because we're getting rid of B as well, I would say a terminal is what you mean, right? So we get rid of a terminal node because we turn it into an internal node. So we -1 terminal node, terminal vert, +2 terminal vertices because we add D and E, and then add 1 internal node because the terminal vert that we lost is going to turn into an internal, right? So vertex B becomes internal, so that adds 1 to the internal count. Vertex B is not terminal anymore, so that subtracts 1 from the terminal count. And then we add 2 to the terminal count because we have to add 2 children to B, right? So in total, we have +1 terminal and +1 internal. They grow at the same rate. And so since we started off with 1 more terminal than internal, and they grow at the same rate, then if we added another couple of kids over here, F and G, well, the same thing would happen. We've lost a terminal node and gained 2, which means in total we've gained 1 of them. And we've also gained 1 internal node, C, right? So because they grow at the same rate, there will always be 1 more terminal than internal. And that's for a full binary tree or a complete binary tree. Now this one happens to be complete, but it was true even when it wasn't complete and we didn't have F and G, the theorem still held, right? So the complete binary trees are a subset of the full binary trees, right? So since it's true for the full trees, it must be true for the complete trees since they're a subset of the full trees. Does that make sense? Questions there? No questions? Okay, so then let's do one more little proof here. Let's do this one for complete binary trees. Oops, helps if you spell it right. Now here I want a formula for the size of the vertex set. Well, let me rephrase this. No, that's the wrong way. Let's say with height of the tree h, right? Let's do a formula for the size of the vertex set in terms of h. So as a function of the tree's height. You get 2 to the height minus 1. 2 to the h minus 1. Okay, let's do a proof. So what kind of a proof should we do here? Inductive, sure, we could do that. So how would that work? So what's our base case going to be? Base case h equals 1, okay? So that would be this situation. Okay, so what is the size of the vertex set? Well, the size of the vertex set should be 2 to the first minus 1. Uh-oh, that's not good. Two to the first minus 1. Yeah, we need a plus 1. Where do we need that plus 1, David? After h, good. There we go, let's try that. So base case, h equals 1. The vertex set would be 2 to the 1 plus 1 quantity minus 1 equals 2 squared minus 1 equals 3. So that works. Okay. So then let's try the inductive case and see if that still works, right? So what are we going to do here? Bear in mind, we can use this previous theorem that we proved if it's helpful. Don't know if it's going to be helpful, but it might be. So what are we doing induction on here? Yeah, very good, Sean. That's perfect. I was just asking, what are we doing induction on? We're doing induction on the height, right? So if we go from height equals 1 to height equals 2, right, then we should be adding, you know, the right amount of leaves in that case, right? We add 2 internal nodes and 2 external every time. Ah, okay. Every time, well, I'm not quite sure what you mean by that, David. Every time what happens? Do we add 2 internal and 2 external? Never mind. So I think for every pair of children that we put on, right, pair of children for one parent, right, each time we do that, we add 1 internal and 1 external. Right, exactly. Yeah, so we add 1 internal and 1 external for every time that we add two children onto what used to be a leaf, and now it's internal and these 2 guys are leaves, right? So, okay, and how many times do we do that for a complete binary tree? Yeah, every subgraph at that level, right? So for every leaf, we add on another leaf and another internal one. So for example, if I had, this situation, and now I want to add a new level, well, for each one of these guys, right, I'm going to add 2 to it, which means for each one of these, what used to be leaves, I'm adding an internal and an external. So I'm adding 2 times the number of leaves here, which is 4, to be 8 total things that I'm adding, right? Yeah, so to make a complete tree, we add twice as many nodes as the previous level, right? So here I had 4, but I'm adding on 8. Okay, so how does that help me? We can apply the formula of full binary tree to this one. I agree, Nathan. How would that work? To calculate the leaf number. Okay, sure. So you want to add up the total vertices, right? Okay, so how is that exactly going to work? Okay, if a complete binary tree is full, then the leaves equal the internal plus 1. Okay, so I'll make a little note here. Leaves equals internal plus 1. Okay, that's what we proved before. Great, so how does that help us? When we do induction on the height, what happens to the old leaves? Okay, so now you're saying the leaves are going to be 2 times the second to last level, because the second to last level here, this would be level 0, 1, 2, and 3. So let me number these. On level 2, we've got 4 nodes, right? Which means on level 3, if each of these 4 has 2 children, it'll be 2 times the number of nodes on level 2, which is 2 times 4 equals 8 nodes in level 3. Okay. So how does that help? I think that's going maybe a different direction than this guy. Maybe not. I don't know. What do you guys think? Okay, for h equals k, we have n leaves. Ooh, I'm not sure what K is here. I'm sorry, Nathan, what's K supposed to be? Okay, we proved that H equals K plus 1. Okay, you want K to be like the current number of leaves. Or, oh, okay, no, you want K to be the current level, right? So here, this would be K, and this would be H. So H equals K plus 1, is that right? Okay, we proved that H equals K plus 1 as the formula. So this formula up here, this one, or a different, we subtract V prime and V. I'm not quite sure what you're getting at there, Nathan. Also, feel free to hop on the mic, anybody, if that would be easier than typing. I assume it would be. It's kind of complicated, right? Okay, so David, you're saying we use the inductive hypothesis. That's a good idea. 2 to the h plus 1. Then we use the fact that the external leaves, the leaves, are 2 to the h, right? So we get 2 to the h, I think times 2. You mean instead of plus 2, you mean 2 to the h times 2 minus 1. Is that right? That plus should be a multiply. Is that right? Oh, or is that plus supposed to go into the, I get it, into parentheses. Yep. Okay, I got it. Very good. Beautiful. So here's what we're doing. Saying, okay, we've got our internal vertices, which we know from the inductive hypothesis are going to be 2 to the h plus 1 minus 1, right? So our internal vertices are going to be 2 to the h plus 1 quantity minus 1. Okay. And we use the fact that the external leaves are 2 to the h. Well, how do we know that? So how do we know that the leaves are 2 to the h? And in fact, I think there would be 2 to the h plus 1, right? Okay, because each node splits every time. So you get 2 for each leaf, right? So for each prior leaf here, you get 2 children, right? So if you had the number of external leaves before is 2 to the h, then you'd have 2 to the h plus 1 leaves, right? So here I'm saying h equals 2, right? And then I'm doing induction and saying, okay, well, what happens if h equals 2? Well, by the inductive hypothesis, all of the nodes before, there are 2 to the h plus 1 minus 1 of them. Now they're all internal, right? Because before we had, sort of this situation, right? Where we only had the stuff above the line, above this little squiggly line, right? And we know that, okay, well, this is the total that we had before. Now those are all going to be internal. And so we can use our inductive hypothesis here to find the total number of internal right? Which means by our previous, right? If we know that we have k internal, then we add 1 to get the number of terminal, right? This is by previous theorem. And to get the total, we add these, which is 2 times 2 to the h plus 1, quantity minus 1, which of course is 2 to the h plus 2, quantity minus 1. See it? Does that make sense? Oh, Nathan, you have a note. Is that what you said? Let's see. Calculate the number of leaves when h equals k. Okay, then calculate the number of leaves when h equals k plus 1. Then the number of leaves when h equals k plus 1 equals 2 times when h equals k. Sure, that's another way of thinking about it, I think. I think that's right. So what do you guys think about this way? Does this way make sense? You know, by the inductive hypothesis that you had this many as the old total, which now they all become internal, right? So all the internal nodes, the internal vertices in the new tree is the total amount from the old tree. We know from our previous theorem that to find the number of leaves in that tree, you take the internal number of vertices and just add 1 to find the leaves, the terminal vertices. So here I've taken that old value, added 1, which just cancels the minus 1. Then we add the internal and the leaves to find the total, which is the formula required. Is everybody happy with this? Does that look good? Yes. Okay, so Nathan, you're into it. Anybody else? Questions, comments, concerns? Makes sense. Nice. Okay, very cool. There's a lot of different ways of proving this. Okay, there's a lot of different ideas for how you can do it. So I definitely recommend thinking about this a little bit. See if you can prove it a different way. There's quite a few ways of doing that. I did want to mention Cayley's theorem real quick before we go, because we didn't get a chance to prove it yet, so we'll have to do that next time. But I can tell you the formula. The number of distinct directed trees with n vertices is equal to the number of trees of different trees with n vertices is equal to n to the n minus 2 power. That's Cayley's formula. So if you need that for that web work question, that's how you can figure that guy out. And we'll prove that next time because we've run out of time. But that does get us all the way through 10.6 at least, so that's good. Any questions on any of that before we go? Okay, sounds good. Well, have a good one, everybody. I will see you on Wednesday. See you later, guys.